Continue our discussion about the bootstrapping. So, what we have done, we have shuffled them. Now, if you see the third column, all of them are basically jumbled up. Now, what we do is that we pick up such random k, say for example 40 number of observations rather than picking up from the lot. So, consider 40 we are observation picking up is x 56, x 265 and so on and so forth. Now, once you have that, you find out the average of that, note it down, again replace in the jumble and again jumble it. Again you randomly pick up such, say for example 40 observations, initially it was also 40, now it is also 40, so 30 can be 30 also, there is no problem. So, and pick up again randomly from different positions, they are already jumbled up. So, if you keep repeating it, what you will have, if you say for example do such 40 number of pickings at each go and you basically pick up k number of them, then the averages of this k number each are totally different. Then what you need to do is that find out the averages of the average and all the characteristics which are needed in order to basically have a good study about the population which you need to study. So, if you note down, you have picked up x1 for this case rather than 30 or 40, I am picking observation 1, 2, 3, 4, 5, 6. This is just an example considering the space of trying to denote in a slide is limited. So, this need not be 5. So, once we find out, we will find out the average from this 5, and what we do is that as you keep up picking up observation, this such 5s and you repeat it, say for example 20 number of times, this is the first 5, this is the second 5, this is the third 5, fourth 5, fifth 5 and so on and so forth, it will continue. Once you find out these averages, they are denoted by x bar 1, x bar 2, so on and so forth, and once you have this, you find out the averages in order to find out the characteristics which are of most important to you. So, for the first one which you find out, these are the characteristics. For the second set, these are the characteristics, third set, these are the characteristics, so on and so forth. So, if you pick up k number of them, you will have such k here, and finding the averages of this, you will get all the characteristics which are the mean, standard deviation, variance, kurtosis, so on and so forth. So, if I am talking about the mean, very simply mean would be, if I pick up n observations, it will be this, and if I repeat it k number of times, so this is say for example j is equal to 1 till k, so what you will have is that this x bar you will calculate the average, and this average would be averaged out more in k number of observations. So, first block of say for example n size, second block n size, third block n size, repeat it this k number of times n, and then find out the averages, and that will give you the actual characteristics. So, now let us show the actual study which we have done considering the Bajaj Auto. This data was taken from the year for the last 3 years till 2015 July. So, once I have this, considering that the boot size which you are going to take is 50, 100, 500, 1000, 10,000, you see the mean plots, the average which you find out, and if you keep repeating it, the average slowly smooths out. So, the overall variance which you have would be there, but it will basically be slowly smoothened out. So, you want to find out what happens to the standard deviation. This is the standard deviation which you have. There is a huge amount fluctuation, but the actual fluctuation tapers down. That is not important. What is important is to note down how does the mean QQ plots and the standard deviation QQ plots vary. QQ plots basically means the variation of the actual variable which you are going to study using the quantile plots. Now, if the underlying assumption is the population distribution is mean, then the mean would by itself for random sample would be distributed by normal distribution with certain standard deviation and certain mean, and the variance would be distributed for the samples which you pick up would be distributed at chi square. So, if you fit the mean distribution of the sample which you are picking out with the standard normal deviate, you will find out as the boot size increases, it becomes exactly a straight line. Similarly, as you pick up for the variance or the sample variance along with the chi square distribution, initially there is fluctuation, but in the long run again we will get a straight line, which means that it basically adheres to the property that from the concept of theoretical concept which we study, that the mean of the sample in the long run would basically be exactly equal to normal distribution, then the chi square is the best fit for the sample variance. So, that actually comes out in this case. This is considering that you are considering for a big sample size and considering the central limit theorem to be true. But if we consider the extreme value distribution, it need not be, but still it gives you a lot of information that if you do the bootstrapping, you can find out the actual characteristics of the population in a big way, considering that you have only one chunk of sample and you resample it repeatedly k number of times, where k can be a very large number. Assumptions of bootstrapping are: bootstrapping makes no assumptions regarding the population, no normality of error terms is considered, it can be anything, no equal variance is considered, it can change, but still we are able to mix it in such a way that the variability is basically done away with, allows for accurate forecast for intermittent demand in between. If the sample is a good approximation of the population, the sampling distribution may be estimated by generating a large number of new samples. That is what I am saying, that if you consider the sample which you picked up at one go actually has lot of information on the population, then trying to repeat picking up the sample in the same manner a number of times would actually give you the whole picture of the population if you combine all the sample informations together, because you are trying to pick up chunks. These chunks are picked up from the population randomly, and if you are able to pick up the chunks in a nice manner, then all the characteristics of the population will be coming out in the combined chunk which you form by combining the samples. For small data sets, taking small repetitive sample of the data and repeating it will yield superior results. That is what I am saying. If you do it with replacement for a large number of such resampling or subsampling, then the characteristics of the sample, considering the sample is the best proxy of the population in a very nice manner, then combining the samples would actually give you a lot of information about the population and its characteristics. Now, with this concept background, I will just cover in a very simple manner what you mean by robust optimization. Now, before I scribble anything, let me again go back to the Markowitz model. In Markowitz model, or generally the actual concept was, given the utility, the actual characteristic of the portfolio is that you have W1, W2, W3, W4, so on and so forth are the weights of so called n. This small n is not exactly equal to the sample size which you have talked about. Consider this n is the number of financial stocks which we have. So, these W1 to Wn are the different type of scripts, and their corresponding mean and the variances are given by r bar I and sigma square I, and the covariance is also known to us. So, we have either formulated the Markowitz model by trying to basically minimize the overall portfolio risk subject to some constraints, or trying to basically maximize the overall return. So, if you minimize the risk or maximize the return, you are trying to basically take two approaches, but the constraints would all be the same. Like if there is the sum of the weights should be 1, then if the weights are between 0 and 1, there is no short selling. If the weights can be negative also, there is short selling, that is unboundedness, all these characteristics. Now, inherently, if you note down whenever I said I considered a priori that given the fact the observations were known, the closing price, they were fixed, they did not change. So, given the closing price, we will consider them to be given, and we will consider the return which is ln of P2 by P1 as being given, and they are deterministic, and based on this we proceed. Now, the problem is these are the past data. So, the past data would not give us exact information on what is going to happen in the future. So, we will consider the past data is a subsample from the overall population and use this past data repeatedly with resampling in order to basically do some good bootstrapping in order to utilize our results. Now, when you are trying to utilize our results, obviously there would be constraints, probability and the constraints. Like say for example, consider very simply, I want to minimize the risk sigma ij, consider the returns are greater than equal to some r star p value and other constraints are there, forget about that. Now, if you looked at it carefully, what we can do is that rather than being having the return on the portfolio being greater than some r star p, we can just put a concept of probability that this value will be greater than r star b by some probability beta 1, which means that if we consider the concept of a non-deterministic case, then there may be some instant where this inequality may hold and this inequality may not hold. So, what we are trying to do is that we are trying to put some probability bounds that if this is say for example 90% and we say this inequality holds 90%, it means that if you keep repeating the experiment, do the simulation 100 number of times, 90 of the instances it will be true, 10 of the instances it would not be. That means, we are slowly trying to bring some non-deterministic nature in our overall concept of trying to solve the optimization problem. So, let us consider the concept of robust optimization and how we proceed in a very simple manner. Now, the advantages of robust optimization is that we do not consider any underlying distribution for that parameter which you are going to study, that it is not specific to any distribution. Because if you consider some specificity of the distribution, then you have to basically consider what type of distribution it holds. Does it hold that is Frickett's distribution? Does it mean that is going to be Gumbel distribution? Or say for example, depending on a different type of problem, should we consider as a normal distribution? Should we consider it as a Weibull distribution? Whatever it is, that would basically come under the purview if we study the concept of reliability based optimization or stochastic optimization, but we in the robust case we will consider the underlying distribution is not taken into consideration. So, in that case your question would be what we consider, rather than distribution we consider a set, that is a set is basically a small bandwidth, like say for example consider an atom is vibrating. So, if it is vibrating is basically the mean value and is vibrating over a number of certain range on the right hand side and the left hand side. So, we will consider some sort of set where the vibrations of the movement of the atom would give you the overall bandwidth between which the overall stock price can fluctuate. So, if the bandwidth is very small, that means the level of probability is very high, that means we are confident that the value of the stock prices would be between a certain bandwidth. If the bandwidth is very large, then the corresponding probability slowly shrinks. So, uncertainty is the way which you are trying to bring for our study in the optimization sense, in the financial optimization sense, where we will consider the input variables are uncertain. So, optimization can be done in stochastic optimization sense, robust optimization sense, there is reliability optimization also we will consider at the fag end of this class, because after the robust I will again switch back to the discussions we are having. And if time permits, I will definitely consider the concept of reliability based optimization, which is also very heavily used in civil engineering and mechanical engineering, but we will try to give some examples where it has been used in financial optimization also. So, advantages of robust optimization over stochastic optimization is probabilistic distribution of the parameters is not required to be known, as I said, it is easier to solve, because once you have the actual mathematical formation, converting that into a programming concept becomes very easy. Robust optimization can also be applied to the allocation of assets in portfolio optimization, which we will consider. The aim is to invest a proportion out of the total money you have in your hand in assets in the stock market to maximize the overall return or minimize the risk or whatever your actual concept is, but with the fact that the input variables are non-deterministic and we would not consider any distribution to be true, and we will consider the concept of set in a very general sense, as that the set will give in a way the overall reliability or the overall of robustness which are there for our answer. So, uncertainty sets, as we know, or if somebody studies are different type. Some of them are the scenario generation, that means we generate the scenarios. There are the polytopic uncertainty sets depending on whatever mathematical assumptions which you have. Then another is basically the box probability and the ball probability. So, if you consider the box and the ball, there are let me step back, and there is a concept of distance measure. In distance measure in simple mathematics is basically the norms, L1 norm, L2 norm, L3 norm, whatever you have. And L2 norm we know is basically the Cartesian coordinate concept which we use when we want to find out the distance between 2 points. Consider the points are x1 and y1 in the 2 dimensional case and x2, y2, we will basically consider x1 minus x2 whole square plus y1 minus y2 whole square root of that. So, this you are taking the L2 norm. So, this is known as the L2 norm as is denoted, and the L infinity norm is basically when we consider the maximum of the distance, and there are concept of L1 norm is which is known as the Manhattan distance, but this is just for the information. We will only concentrate on the Cartesian coordinate L2 norm and the infinity norm, which is in the robust sense is known as technically the ball or the ellipsoidal uncertainty, and it is known as the box uncertainty for the infinite norm. Ellipsoidal is basically the ellipsoid which you are forming in a higher dimension. If you consider in the simple 3 dimension, and if all the variances are equal, then it is basically a simple football shaped, and if you consider the variances are different, is basically a simple like a rugby ball if you see, and as you go into a higher dimension it will basically ellipsoid, like means in a 2 dimension is basically ellipse rather than a circle, and in the higher dimension rather than a football it is basically a simple base this rugby ball which we consider, which is the American football. Now, in the box uncertainty, the box is denoted by, as we know, in a 2 dimensional by this. In a 3 dimensional it will be a cube, and in the ball one, if you do in a 1 and 2 dimension is a circle, and in the higher dimension is a sphere. So, what we do is that we want to basically find out the common area between the box and the ball. So, once you are able to find out the common area between the box and the ball, it gives us the maximum reliability based on which we can do the study. This is the very simple concept which we would not go into details in order to explain the mathematical concept. It is basically a union of this, and we find out the intersection such that it gives us the maximum probability of the reliability. Now, the study which we do, as you remember, I mentioned about 3 years. So, these are the data sets. The data sets which we are using are the BSE in the Bombay, DAX in Germany, Dow Jones Industrial Average, DJI, Hang Seng which is HSI, STI is the Singapore one. Companies have been taken, all the indices which are there in this index for 3 years and 1 month starting from January 1st, 2012 to January 1st, 2015. We took a window size of 150 with 50 days overlapping. They were overlapping each other, that is 100 days of shifting window. The window size of 150 signifies significant 6 months seasonality which may be there in the stock market, and the overlapping window is considered like this. It shifts. So, repeat in bootstrapping you repeated the data 25 number of times and merge them together in order to do the bootstrapping concept which we have considered. Window lengths of 5 days and found window length of 5 days has also been taken, and we have done the bootstrapping considering 500, 1000, 2000 so number of n boot. The objective of the portfolio optimization theory consists of selection of the assets in such a way that you are able to maximize or minimize some objective function. If you assume there are 2 trading periods, the initial trading period is 0 and the final trading period is t. In between it will be 1, 2, 3, 4 till t minus 1 and then the t. Let the total number of n random assets being there and the returns be calculated given by ln of pt by p0 or pt1 by pt2 and so on and so forth. Investments can be characterized by n cross 1 vector which is w1, w2 till wn, which are the weights. And the goal of the optimal allocation is to select the optimal vector w that gives the best final worth, whatever the concept of best is. So, let us consider these notations without going into technicalities. R star is the return of the I stock, xi is the weight assigned to different stocks which is the w's, xt is the vector x1 to xn depending on which time period you are considering, that time windows we considered, the number of stocks. Ni is the number of stocks, Nt is the number of stocks given in a vector, capital N the total number of stocks, sigma I, rho sigma ij, rho ij are the corresponding standard deviation, covariance and the correlation coefficient. Then these are the level of risk considering different concept of robustness we will consider. Q is basically the variance covariance matrix. Then you have the T as the time period, and this var threshold value. What is var will come to that later on. Later on means another 3 or 4 lectures will be there into var and C var and so on and so forth. Rho and this positive deviation the portfolio, the negative deviation the portfolio, the the shortfall of the portfolio, all things would be specified depending on what you think of the level of your reliability is. And this Q star or Q0 is basically the initial deviation over and over which the reliability would be. That means, if you remember, I mentioned the center and over which the fluctuation is. So, this is the mean value which you are considering, which is denoted with is one of them is here and another one would basically be the R bar 0 I for the stock which you are considering. So, the first model is we consider the model where we minimize the risk corresponding to the returns being greater than or equal to R p star, and sigmas and the sum of the weights is equal to 1, and such that the stocks are is equal to 1 to n. So, if you do the risk return comparison and do the runs for different levels of reliability starting from the deterministic one, for the 90% reliability, that means 90, 91, 92, 93, 94, so on and so forth of the beta value which we consider for BSc are shown accordingly. We will end the class here, and if you consider later on, we will discuss the models in detail as we discuss the runs in much more details later on, once we basically finish out the discussions about different concepts which you have to cover. Thank you.